Hello, welcome to another problem session. Today we have a really interesting problem. I think you probably know Atwood machine from your book. This is a very standard problem. This is the problem where you have a pulley and you have one block M1, another block M2. So these are blocks, and this string, its length L0 is fixed. It's not changing, and this thing is hanging like that. So this is the Atwood machine. This is just one T Atwood machine. Okay. So what do we here? Actually, this is an extension of Atwood machine, if you like. So you have the block, you have the pulley, but on the other side you have a disc where has a tape. It can unwind, and so this length of this tape is actually, as it unwinds, it can change. So this L is a function of time, unlike over here. So some of the quantities will be related a little differently here. So here, if this is A1 and this is A2, then A1 equals to A2. Or if you call this side A1 and also acceleration A2, this A2 prime, then A1 plus A2 prime has to be 0. And that came from, if you took how far away all these strings are, so length of the string plus this, which is common, so I'm not going to worry about that. So if this is, say, y1 and this is y2, then you had a y1 plus y2, so all the axis, y-axis is down, y2. So the L0 is this plus pi times r. And so this is fixed. So if you take a derivatives, L0 double dot equal to 0 equals y1 double dot plus y2 double dot. And this is the one we're calling A1, and this A1 A2 prime, and that's equal to 0. And that's what that comes from. But now this length is, in this case, is not the same. So it's going to be different, right? So I'm gonna do a very similar thing as this on here. Okay, so let me pause and clean. So over here, let's see if you do exactly the same thing as before, then we are going to have this distance. Let's call this from here to here is y1, and from here to here up to that point y2, just like before. And so you have a y1 plus y2, and part of that y2, this is at time LT. But if you look at y2, then there was at time 0, say you had a y1 0 plus y2 0 equal to some L0. So if I look at it, I will have a L I kind of forgot that pi times r1. So I'll put this. So you have this, and if I look at some of this must have come from unwinding of this. So if this thing unwound by delta theta 2, then we will say that y1, let's look at this. So this will be something that happened here, L0, and it extended because this kind of unwound. L0 plus pi times, not pi times, R2 times delta theta 2. So however much it unwounded in time t. So this is, you can just say theta 2 at t, and theta 2 0 is 0. So this is the amount it unwinded of unwinding of disk. So if you take time derivatives of these things, so y1 double dot plus y2 double dot, 2 time derivatives, dot is d by dt. So this is 2 time derivatives plus 0 on this side, and so on this side we're going to have so on this side we're going to get L0, we're going to get a 0, and then this R2 alpha 2. And we are going to write down this as this is what A is, and this is going to be all down, axis is down, so this is capital A, and this is R2 alpha 2. So that's one relationship. Now if you look at rotation of this and movement of y1 will tell us how much I mean, this thing can go down. As it going down, is the tape has to rotate this pulley down here. So this is delta theta 1. So we have y1 that we can just choose that to be 0. y1 movement in delta time t must be equal to r1 delta theta 1. So if I take a 2 time derivatives of this, d square dt square, this will become A will come to R2 R1 alpha 1. So these are the relations we seek, that part A. Okay, so I'm gonna clean this up and get the part. Okay, so for part B, we are going to set up equation of motion, equations of motion. So we have a whole bunch of equations of motion. One is a translation of the block, and that's going to be it simply is going to be based on, let's call tension here T1 and tension here T2. So you have a tension pulling up and M1G pulling down, and its acceleration, we've taken that to be the positive direction. So this will just give me M1G minus T1 equals M1A, and this is equation 3. So this is equation 3. Another equation will be translation of the center of mass of this thing. So 2a, for this we'll have a translation and a rotation problem. So translation of center of mass of Cm. And so let's look at the forces. So there is there's nothing holding it here, so there's no force like that. Normally you will have a force like that, so there's no force like that. This thing is unwinding, but the tape, there's a tape with a tension T2 here and M2G this way. So the center of mass is basically a free body diagram. Free body diagram will be simply T2 and M2G, and as a result is going an acceleration capital A. Taking A as positive downward. So this gives me M2G minus T2 equals M2 capital A. Question 4. And then we have a rotation about axis through Cm. So here's the axis. Here's the axis about which it is rotating this way. So you can see that this has no torque. So torque of M2G is 0. And that means it's only torque is from here, and this is R2, and alpha is in this direction, alpha 2 is defined in that direction, and torque from T2 is also in the same direction, same sense. So this will give me T2 R2 equals to I through this axis and through Cm, and then alpha 2, and this guy is about this axis, and the disk formula is half M2 R2 square. So you can see that one of the R2 cancels this, and alpha 1, this alpha 2, I'm sorry, this alpha 2 will be R2 alpha 2 will be A plus A. So this whole thing becomes T2 equals half M2 A plus capital A from here using 1. So this is our equation number 5. We have a whole bunch of equations. We're done with this. This is for the block, and this is for the this disk. And for the pulley, if you look at the pulley, it's just a rotation. So the pulley has a tension going down, this one, and this tension 2 is going down. There's mg, and there is a normal. And the whole thing, we are doing alpha 1 that direction. So from here, you can see the torque, etc. will be, this will give me T1 R minus T2 R equals to I axis alpha 1, and this is half M R1 square M1 R1 square alpha 1. And this, you can see this is R1s, and this guy cancels out. and R1 alpha 1 is just A, so this is going to be T1 minus T2 equals half M1A. So this is equation number 6. Okay, so I wrote these problems out here, wrote all the equations out here. So now we can try to see how to solve it. To solve B, solve for B, we need to work with these equations 3 to 6. We can see that we want to find expressions of this, and we're not interested in tension, so we'll eliminate T1 and T2 and get two equations in A and A. Okay, so one way to do it is let me kind of work through it. It's going to be pretty a lot of work, but we can do it. Say equation 3 minus equation 4 plus equation 6. That's going to eliminate T1, T2. So it's going to get me M1G and minus M2G, and then that should be equal to, on the right side is going to give me M1A minus M2A. So M1 should be capital M1. Let me see, this one is little m, and that's a little m, and this is M2 and M1. So little m, there's a mistake there, MA minus M2A, and then coming from the pulley plus M1 over 2 small a. So these are together. So this equation you can say is M plus capital M1 over 2a minus M2a, and this is M1 minus M2g. So let's call this equation 7, and I have a T2 here. If I put in here, then I'll get an equation in another equation, little a and capital A, right? So that's 5 into 4, that gives me M2G minus half M2A minus half M2 capital A. On the right side is M2 capital A. These are all capital M's. This is the only small m. And now we can arrange it, and so we will get M2G equals to half M2A plus 3 half M2A. So now we can see that we can get rid of capital A by equation 7 times 3 half and then add to equation 8. So on the left side I got a 3 half M1G minus 3 half M2G plus M2G on the left side. On the right side I got 3 half M plus M1 over 2A plus is going to be plus from the 8 just add it, so this is half M2A. So on the right side you have 3/2 m plus 3/4 m1 plus half m2, and a on the left side you have a 3/2 m1 minus half m2 g. Now therefore we're gonna get a equals to, you can see the half all cancels out, so 3 m1 minus m2 g over 3 this m, not, you see this is mg, this was m, this was m, not m1, and this was m, so this is m, 3m plus 3/2 m1 plus m2. So this is going to be acceleration, and we can plug into this to get a. Capital A will be this 5 into 4, this is all m2, so this is m2, yeah, same m2. A is going to be this minus that, so 2/3 m2 m2g minus half m2a, and of course m2's are cancelled out here, and we have a g minus half a, so you go over there. So now I'm not going to complete this work for you, you can put it in here. Of course the m's are cancelled out here and simplify, so this gives a. So I have a and capital A. Now if I put this into 1, a into 1, get alpha 2, a in 2, get alpha 1. Okay, I think that's a lot of work to get these calculations, and you can see there are a lot of mistake of copying symbols, so it's kind of important to have a good set of symbols, and it kind of makes sense when I go back look at it. You can see that this is what's driving the motion, right, in terms of the difference in the weights. So this unwinding here is actually just one factor, then this thing actually 3 times, or if you pull 3, then this is 1/3 only in terms of on the other side. In the case of Atwood machine, we had a much simpler setting. So in terms of Atwood machine, what drove was m1 minus m2g. So it was just m1 minus m2g that was responsible for the acceleration that was happening. Here actually is 3m minus m2. Denominator is also kind of a little more complicated than that. Here the denominator was like there's one acceleration, and the denominator was m1 plus m2 plus like half capital M. So there are differences that that appear. Okay, so I think that's it. I'm going to stop here and I'll see you in another video.